So coming to my video, welcome guys. Today let's see what are microwave applications. Let's go with wireless communication. So wireless communication is one of the microwave application where wireless system include broadcast radios and television, cellular telephone and network system, direct broadcast satellites, that is DBS, television services. Next, like wireless local area networks, WLAN, paging system, global positioning system service, that is GPS, and radio frequency identification, that is RFID. So basically RFID you will be looking in the shopping malls, right? So in the shopping malls all the clothes and objects will be having a tag, so the tag is an RFID basically. Okay, and now what happens here, there will be a source that is connected to antenna. The source will transmit a wave that which has a power T, and this transmitting antenna has a gain of GT, and the receiving antenna has a gain of GR, and it receives a power of PR, a basic radio system basically this is. So in general the radio link is shown in the above, and whereas the transmit power PT, yeah, I told you, right? So basically this received power will have a resistor, that is a load basically, which will absorb that received power. Now coming to the Friis formula, the power density radiated by an isotropic antenna. For isotropic antenna, directivity is 1. Okay, at a distance R is given by S average, that is power density radiated power density, or S average is given is equals to PT by 4 pi R square, watts per meter square, because it is power density, that's a power by meter square. If the transmit antenna has a directivity gain greater than 0 dB, we can find the radiated power density by multiplying the directivity, That means what he's saying is, if the transmit antenna has a gain G, then we will multiply that gain also here. Basically for an isotropic antenna the gain will be 1, but in general it is an ideal, right? In practical there will be gain for an antenna. So let for suppose the transmitting gain is GT, then we will multiply this with GT PT by 4 pi R square. So that is this. S average will become this one. Okay, so since the directivity is defined as the ratio of actual radiation intensity to the equivalent isotropic radiation, in addition, if the transmit antenna has lossless, we can include the radiation efficiency factor with which has the effect of the converting directivity to gain. Thus the general expression for a power density related by an arbitrary transmitting antenna. So this is the main formula, that is the power density of a radiating antenna is G1 P1 by 4 pi R square. Okay, P1 is the transmitted power and GT is the transmitter gain. If this power density is incident on a receiver antenna, we can use the concept of effective aperture area to find the received power. Since we know that received power in terms of we know a relation between received power and the power density, right? PR is equals to effective area into S average. So that's the same way. So to find the receiver power, PR is equals to S average, where S average is the received power. This is the power density and PR is the received power. So when you use this equation where S average is already known, that is GT PT by 4 pi R square, that we substitute here GT PT AE by 4 pi R square. So where AE is, we know that AE is equals to D lambda square by 4 pi. When you substitute this one, so again the possibility of loss in the receiver antenna can be accounted by using a gain rather than the directivity. That means he is saying that instead of using directivity, we will use gain only. So since A is depending on the D, we just replace A with some other value. Okay, we are replacing A with some gain, and in terms of gain. So then the final result of the receiver power is this one. gt gr lambda square by 4 pi r square pt, okay, watts. So this is the total received power. This is the Friis radio link formula. So as can be seen from the Friis formula, the receiver power is proportional to the product PTGT. There PTGT you can see, right? So basically the received power is depending on the power transmitter and the gain of the transmitter, the product. So these two factors will help determine how much will be the received power. Okay, if you want to increase this product, either we can increase the received transmitter power, or we can increase the gain, or we can increase the both. Now, thus the product is defined as the effective isotropic radiation power, radiated power. So actually, this product is determining the effect, how much received power will be there. No, that's a PT into GT will be termed as effective isotropic radiated power, PT GT. That units is watts. For a given frequency range and receiver antenna, again the receiver power is proportional to EIRP of the transmitted and can be increased by increasing the EIRP. So that's what we can increase. If we increase PT, the product value, if we increase, the receiver power will also increase. So that's what this is a numerical. And so for knowing the numerical, there are few formulas where we can see the effective temperature and all. These how we got in the noise chapter video I have told already. Okay. This is also over. And coming to the radio radar systems. So this is the second application. One application we have seen is wireless communication. Now second application is radar system. So radar or dielectric, so radar system, that is radar or radio detection and ranging, is the oldest application of microwave technology, dating back to the World War II. In this basic operation, the transmitter sends out a signal which is partly reflected by distant target and then detected by a sensitive receiver. So if you want a depth knowledge, like how briefly how and a clear explanation, you can see the in my radar playlist. You can see the first video. Okay, so basically I will give a general how it will be. So basically there will be radar. In this radar it will generate pulses. Basically it will generate pulse, basically pencil beams. Already we know what is a pencil beam. That is, it will have a narrow narrow beam width. It will be very thin. Okay, so it will be generated like pencil beams. It will hit an object and reflect back. Those will be reflected back to this antenna. So this is how the radar works. So at what angle it is received and all, it will calculate and it determines where the position of the object. So that's what he is saying. So basically this is same thing. Actually while transmitting, that will be PT transmits. It will transmit a power in radar. Basically the receiver generally both transmitter and receiver are connected to the same antenna. There is one more case also, that is where we will have two things, one transmitter and one receiver separately. So this type of antennas are also used and this type of antennas are used. So in this type of antenna where we are using separately two transmitter and receiver, those are used in military purpose or missile guiding and all we will use. So those so basically those are called monostatic and bistatic. 1 minute. And okay, so this is called monostatic, where both transmitter and receiver are connected to the same antenna. This is bistatic, where one is active, one is the transmitter and another separately. So this is what, and let us see, these are few applications, civilian applications. We can pause the video and you can read. And military applications. Next scientific applications. So coming to the radar equation, as I told, there are two types. One is monostatic and bistatic. Two separate, in bistatic I told two separate antennas will be there, two for transmitting and receiving. So in general in general we will take only monostatic only. Separate antennas sometimes we achieved. Okay, so now what happens, basically how it works is, there will be a transmitter here, this is a transmitter and this is a receiver, that is both are connected to same antenna. So what should happen basically when power is transmitted to, when something is transmitting, only it should go to antenna, not go to this connection. When something is received, it should collected by the receiver, not by the transmitter, right? Only transmitted to antenna, antenna to receiver, only that should happen. So how to achieve that? By using a circulator. This circulator we already discussed in the microwave devices. So how it works, you can see that. And so this is the circulator, where basically the circulator is like for example, this is 3-port circulator. It is a clockwise circulator, that is like a 1 2, for instance let us take like this. So basically when a signal is from 3, it will only go to 3 to 1, not from 3 to 2. If the signal is at 1, it will go to 2, it will 2 to 3, like that only it will go, not in the reverse direction. So that's what. So when the signal is coming to here, it will go to this antenna. When the signal is coming to antenna, it will go to only receiver, like that. So this is the this is monostatic. It is now it is come to bistatic. Bistatic will be separate antennas for receiving and transmitting. So basically we know that ST is PTG by 4 pi square, that is the power density. We already seen that, where R is the distance of the target. Now basically what happens in radar, it is actually hitting an object and coming back, right? So basically what happens while hitting, not what happens is, if it suppose it is an object, when I try to take this and hit here, it will split basically. Okay, this beam will split into small portions. Basically if the power is 100 watts, if it is equally splitted into 10 pieces, each part will be 10 watts, like that. So only few of these waves will reached by the antenna. So how many will be reached to this antenna are actually determined by the shape of this object. Okay, so that's what we call it as radar cross section, the shape. Okay, basically we are defining the shape in terms of radar cross section, shape of the target in terms of radar cross section. Okay, so that radar cross section is termed as PS, that is where PS is the total power scattered by the target. That means how much here, totally 100, right? 100 total, all the power added is 100. So 100 divided by ST. ST is the average is the power density of the target. So okay, basically power density incident on the target. Okay, how much power density is incident on the target, and is the power density incident on target. You can think that all the next the radar cross, basically what to define is ST is basically how much power it is collected by this antenna. Okay, for example only 2 means 20, right? 20 by 100, like that. So next it depends on the how actually this sigma will be depending on the radar cross section, the dimensionless area. So dimensionless. So because both are powers, right? And sorry, the radar cross section has the dimension area. So radar cross section has the units and meter square. Okay, and it's basically actually depends on the inclination and the reflection angles. So because for example the object is like this, if the rays are coming like this, and it will direct like this, right? So if the radar is like this, only one is coming. If the radar is like this, and a transmitter like this, all if it is rays are incident perpendicularly, then all the rays will come back. So that's what incident and reflected angles and polarization of incident and reflected waves. So basically how incident and reflected angles is like this one, how much it is reflecting, and in polarization is how in what orientation the signal is being hit. Okay, next since the target scatters as a source of finite size, the power density of the radiated field must decay as 1 by 4 pi whole r square. So by using that, what is thus the power density of a scattered power back to the receiver antenna must be. So SR is equals to PT into G sigma. So G into PT into G into sigma by 4 pi r whole square. So where sigma is PS by ST, where from that all we substituted as PS, you know, and ST we know, that's all substituted, we got SR is equal to this formula. Okay, the power density of a scattered field. So by using this SR, we are actually finding the what is the received power. So received power is by substituting SR, so in that actually this SR we got now, we substituted this SR in the PR equations, what we got above. Okay, so in this actually no, I think no need of derivations, basically the formulas are important. Okay, what is the radar equation and all. So PR is equals to PT G square lambda square sigma by 4 pi whole cube R power 4. So note that the receiver power varies as 1 by R power 4, which implies that the high power transmitter has a sensitive low power receiver. So that's what. That means if the R value is increasing on basically that if the distance, the target is so far, then what happens, the signal has to travel to that much distance and come back. No, then it will be very small. That due to noises, what happens, due to scattering and noise, what happened, the signal, received signal will be so small. Even that so small signal should has to be detected by the receiver. So that's what. If a transmitter having a high power, then it will get if the transmitter is having high power, it definitely goes to. So since the transmitter has the high power, right, so as it has high power, it can basically that wave can travel long distance. So if it is able to travel long distance, that means it will have effect of noise will be more and the received power will be very less. So even though the receiver should has to detect that small power. So basically this is the radar equation. Received power equation is this, PT G square lambda square sigma by 4 pi whole cube R power 4. So where we are, this is the formula. Now we have to write, we are same rearranging and finding in terms of range. So basically here you are seeing an Rmax, and instead of PR we are writing Pmin, that means minimum power. So basically what happens, a receiver can only detect up to some point, right? Suppose at 1 milliwatt only it can detect, up to 1 milliwatt only it can detect, below 1 milliwatt it can't detect. So that point is called minimum power. So when at that minimum power, when you use that minimum power, we'll get what happens, we'll get range, that is the maximum range it can detect. Basically if the range is exceeding that, it will travel to some extent and it will come back. While coming back, the received power will be less than that minimum power that it can detect. So that's why what happens, it can't detect that minimum power, that power received. You understand it? So basically the range value when the received power is the minimum power that it can detect is called maximum range. Okay. So this is what, so these are the numericals. So here in the next chapter we will see what are microwave resonators. So thank you for watching. Like, share and subscribe.